Welcome back to another explainer. Today, we're diving deep into the finite bytes of our system architectures, and, you guessed it, we're moving way beyond the textbook. We are basically going to perform a forensic autopsy on standard Java syntax. Why? Because we need to uncover those hidden compiler transformations that can and absolutely will silently crash your application in production. We're looking straight under the hood, right down to the bytecode level. Now, it's super easy to just assume that what you type in your IDE is exactly what the JVM executes, right? Well, not quite. We're going to challenge that textbook narrative that logical grouping tools, things like nested classes or enums, are just harmless structural conveniences. They aren't. By actually decompiling these structures, we'll reveal the severe runtime taxes and memory starvation vectors they secretly impose on your apps. Here is our diagnostic blueprint for today. We've got the implicit pointer leak, the enum allocation tax, the resilient singleton invariant, markers versus runtime annotations, and finally, we'll wrap up by resolving the thread trap. All right, let's start dissecting. Part 1, the implicit pointer leak, uncovering the this0 reference. So, on the surface, non-static inner classes look like a perfectly clean way to encapsulate helper logic, don't they? But beneath the syntax, they're hiding a pretty dangerous secret. You see, the compiler quietly intervenes at build time, and it injects this phantom pointer named this.0. This fundamentally alters the generated bytecode, basically forcing your inner class to permanently capture and bind to its outer instance. Now, sure, this is exactly how the inner class sees those private variables, but man, it comes with a massive risk. Let's look at how this actually breaks production. If you take this non-static inner worker and pass it to a long-lived system component, like say an asynchronous thread pull task executor, or maybe a static event listener, that this zero-strong reference goes right along with it. And the result? It traps the entire outer container in memory indefinitely, even if your main application thread completely drops all references to that outer object. The garbage collector is completely blocked from cleaning it up. This right here is what sparks a severe, completely silent memory leak. Now, to protect your JVM heap, we need to contrast this with static nested classes. Simply marking that nested structure as static totally severs that implicit connection. Static nested classes operate cleanly. They basically behave exactly like top-level classes without any of those hidden outer links. So this enforces safe memory isolation lines and entirely eliminates that risk of hidden heap degradation. Moving on to part 2, the enum allocation tax, decompiling the clinit block. Look, we all use simple enums every single day, but decompiling them actually exposes a very explicit memory tax. When you declare an enum, you aren't just making a simple list. The compiler is actually in the background synthesizing a fully realized final class that extends java.lang enum. It then initializes those constants within a static initialization block, the clinit block, and it injects a private backing array named $values just to hold them. Now, what's truly fascinating about this setup is how the compiler has to protect that backing array, because it absolutely must prevent any malicious external manipulation, like, some code accidentally overriding an enum constant. The generated values method is forced to return a brand new, shallow clone of that values array on every single invocation, every single time. And here is the trap, folks. If you execute this clone generation inside a high-frequency message processing loop, it means you are literally instantiating millions of short-lived array objects completely unnecessarily. You're just flooding the young generation heap space and triggering frequent minor garbage collection pauses. So how do senior engineers fix this? They remedy it by calling values just once, caching those constants in a local static immutable list, and completely bypassing that allocation tax. All right, part 3, the resilient singleton invariant, JVM-level corporate cracking immunities. You see, enums aren't just about constants. They actually provide a fortress-like advantage. They act as the absolute most resilient pattern for building Java singletons. Why? Because enums provide native JVM-level immunities against standard corporate cracking vectors. Say an attacker tries a reflection engine attack using constructor.setAccessibleTrue, well, the reflection engine just intercepts it and natively throws an argumentation exception. No way in. What if they attempt a serialization attack, trying to duplicate the instance via deserialization workflows? The JVM natively steps in there too, only serializing the string identifier name and safely binding it right back to the exact unique class instance managed by the class loader. It is literally bulletproof. Part 4, Markers versus Runtime Annotations, Compile Time Safety versus Metadata Agility. When structural tagging is required in your system, you face a really distinct architectural trade-off. Marker interfaces, like serializable, contain absolutely no fields, right? They map directly into the type system, which allows you to enforce constraints at compile time via generic bounds. Plus, you get that instantaneous bitwise instantiate of check, super fast. Custom annotations, on the other hand, offer fantastic declarative metadata agility. But beware, evaluating them at runtime introduces minor processing overhead because the system has to execute reflection routines like, is annotation present? It's a small tax, but it's there. And finally, Part 5, Resolving the Thread Trap, the forensic autopsy of a 10-minute freeze. Okay, this is where theory actually meets a production outage. Let's trace the retention graph here. Imagine you have an anonymous inner class executing a 10-minute thread freeze, like a sleep command. That active thread acts as a foundational garbage collection route, and it maintains a strong reference to its target anonymous runnable instance. Now, because that runnable is non-static, it carries that hidden this $0 pointer we exposed earlier. That phantom pointer points right back to the parent cache manager instance, which in turn anchors a massive 50-megabyte payload array. So memory reclamation is completely blocked for that entire 10 minutes, even if you set the main reference to null. The thread is keeping the whole shebang alive. So, the crucial point I want you to take away is this. Knowing how to write Java syntax, that's just the baseline. Truly understanding these lower-level compiler injections, the bytecode translations, and the actual heap retention paths, that is what elevates standard coding into memory-disciplined, production-stable architecture. As we wrap up this explainer, I want you to ask yourself, how many hidden phantom pointers currently exist in your codebase? Are your logically grouped structures secretly taxing your JVM heap right now? Seriously, take a look under the hood of your own projects today and see what the compiler has been hiding from you all this time. Thanks for joining me on this deep dive, and I'll catch you in the next one.